Welcome to my new calculus channel. My name is John Gabriel. And in today's lecture, which is lecture 4, we'll be looking at the chapter in my book, my ebook called There Are No Axioms or Postulates in Mathematics. So what we'll do is talk a little bit about the history and then look at how we can actually derive those supposedly axioms, but they're not really axioms. They're actually 5 requirements which were stated by Euclid and which have been misunderstood by the morons in mainstream academia over the past 2,300 years. So let's begin. Now, the first thing I'd like to say is that Euclid's Elements, in particular the first book, is the least understood of all 13 books. I mean, you'll see textbooks stating that a point is not a well-defined object and that we have to accept that it is well-formed on faith or belief. In other words, an axiom. Did you know that the word axiom and postulate, both of those words, were not used anywhere in any of the 13 books of Euclid's Elements, and that the ideas were very strongly influenced by the translators, in particular Sir Thomas Heath, who translated the word "itistho" as "let it have been postulated," but that's not the case at all. So, at any rate, Euclid stated 5 requirements, and he also stated the 5 common notions, right? And the common notions are these 5 common notions here. Now, if you look at these carefully, they're very self-explanatory, and they make sense even to somebody who doesn't know anything about mathematics. This is the most common logic that you can find anywhere in the universe, okay? And they're all very well defined. Okay, a thing is an object. Doesn't matter what that object is. Very well. Now, let's just quickly read through them and see what they say. Objects equal to the same object are also equal to one another. That's as clear as daylight, isn't it? It doesn't matter what the object is. It can be a tangible object or an intangible object. It doesn't have any particular constraint to that definition. Number 2, and if equal objects, in other words, are added to equal objects, if we collect equal objects and put them together, then the wholes or the collections are equal, right? And if equal objects are subtracted, these 2 notions here can be just added into one notion by saying that if the same objects are changed in the same way, then they're still the same object. So and number 4 says, and things coinciding with one another, and objects coinciding with one another are equal to one another. And finally, the last one is not even necessary because it says the whole is greater than the part of the object. So they're all pretty straightforward. Now, these 5 objects were replaced by this hogwash, Zermelo-Fraenkel axioms, okay? And so initially, we didn't even have all of these. For example, initially, we didn't even have the axiom of foundation and the axiom of choice. And these are belief axioms. Also, the axiom of infinity was initially all we had were these first 5, and then they found out that there were contradictions and paradoxes, so they added in some beliefs, the axiom of infinity, replacement, foundation, and choice. Okay, so this is all a whole load of rubbish, which has no place in mathematics, does not replace the sound foundation of Euclid's Elements, which are these common notions, and the way Euclid stated the 5 requirements, which are not postulates, by the way. This Greek word here, etimata, does not mean postulates. It means claims or requirements, okay? So my intellectual inferiors of the past 2,300 years have messed up things pretty badly by propagating or advocating this absolute bullshit that you see in front of you here, okay? And I can tell you, this here has so many contradictions, so many paradoxes. It is the biggest rot that was ever invented by mankind. And I can promise you that no alien would come up with this from nothing, because it's not well-formed knowledge. On the other hand, well-formed knowledge can be discovered by any alien in any other world. It doesn't have to be invented. Well-formed knowledge is never invented, it's always discovered. So, most set theorists don't even understand the very set theory they propagate. They don't even understand that a set is never defined. There is no definition for set. How do I know? Well, I go to one of the lecturers who is acclaimed. His name is Friedrich Schuler. It's this guy here. And you can see his video at this link. And this is what he says. The epsilon relation. So he starts off by saying set theory is built on the postulate that there is a fundamental relation called epsilon. In other words, epsilon is a predicate that binds two variables in order to form a statement. Okay, so even the relation isn't stated specifically, but in fact it's implied. It means one of two things. That relation, it means one of the variables is either an element of the other, or they're both sets. And we don't know what a set is at this time, because there will be no definition of what E is or of what a set is. Instead, we have 9 axioms that speak of the element and sets. So you can only speak of these objects. You can't even define them. And the 9 axioms are stated here by the first letters that you see here. E, E, perp, I, C, F. And that's how Schuler remembers the axioms. So the first one is extensionality. The unordered pair, which is this one here, he's called it E. And all the rest of them, the axiom of subsets, sum set, power set, infinity, etc. So this load of rot is what you have to believe in, and you never really know what is a set unless it conforms to all these nine axioms. And the problem is that it may not be a set, and then you'd have something called the challenge of the problematic set, which is also discussed in this particular video. And I don't want to spend time on it because it's rot and doesn't lead anywhere. There is nothing useful about all this theory. It doesn't replace the foundations, the solid foundations, which are Euclid's elements, okay? If I were you and you're seriously thinking of studying mathematics, I would watch this entire video. It's very enlightening. It actually reveals to you what rot has been advocated by the mathematicians of the mainstream in the last 200 to 300 years. And of course, these illogical ideas, completely illogical ideas, started with George Cantor, who's probably worth a study once, but don't even try to make sense of anything Cantor says beyond his theorem of sets being countable. And that's about as logical as he could get. Anything after that is completely illogical. So I don't want to spend too much time on this useless rot. I'd rather just continue on what is important. So let's just close this and get it out of the way because it doesn't matter. And now I'll go back to Euclid's elements. So what I'm going to deal with today is the fact that these 5 requirements can be derived from nothing. In other words, from scratch. You don't need to believe that a straight line can be drawn from any point to any other point. You don't need to believe that a point is an ill-defined object. It's not. It's very well defined. And it wasn't defined that way incidentally. It was defined that way on purpose by the ancient Greeks. Now, if you try to translate this in Google Translate or any other Greek lexicon, it's not clear what it means. So let's just try and do it. Okay, I'm going to basically read this out because I don't want to copy it, and let's see what it comes up with here. Okay, so let's turn this on. It is though. See, even that's not right. Let's just clear that again. It doesn't recognize the word it is though. It is though. Από παντός σημείου επί παν σημείων ευθεία γραμμήν αγάγιν. Okay, so you can see that it doesn't even recognize some of those words. For example, itisto, I don't know what the modern Greek word for that is. And agaion sounds like it has its roots in the Greek word paragogoi, which means production. Okay, so this here stated, or attempted translation, even in something like Google Translate, doesn't really amount to anything. If you look on the right here, it says, from any point straight line. So this is how it was with ancient Greek. If the meaning was understood, they would leave out whole chunks of the sentence. So for example, από παντός σημείο, from any point to any other point, straight line produced. So you see, it doesn't even say what it says here in the English. So in actual fact, when you think about this, you have to remember that Heath was translating from a language which wasn't his first language. And even Greeks who are fluent in ancient Greek don't know how to translate this correctly if they don't have a strong background in mathematics. In fact, I've asked several professors and they've not been able to tell me what this word means in ancient Greek or in modern Greek. So as far as I'm concerned, I've actually proved that it doesn't mean let it have been postulate or there are axioms in mathematics. It doesn't mean that. These are not axioms. Atimata is not an axiom. And in fact, the word axiom doesn't appear in any of the 13 books, neither does the word postulate. All right? And kine enoi, in fact, that's kine and ni-e. Kine and ni-e means common notions. But it doesn't have anything to do with axioms or postulates either. So my purpose is to talk about these 5 requirements today. I'm not going to spend too much time on this book anymore because it's not important, except to know that the ancient Greeks knew that these could be derived from nothing. And so they stated them because it was obvious to them that these were not beliefs or statements that required faith or belief. So let's go back to the book. Now, in this chapter here, I show you that the 5 requirements, or the atimata, have been misunderstood. And so you can read through this first part. It's interesting. It contains some interesting information about the background and the history. And also shows you how it could have influenced mathematics if it were understood correctly. Okay, so let's just continue with the 5 requirements that can be systematically derived. And we start off with the idea of a point. It's simply the concept of location or place, and it arises instantly when the question where is asked. Okay, so in a void universe, location is not possible to reify. There is no frame of reference or a means of describing, in other words, a coordinate system, any given location exactly. How did the Greeks overcome this? Well, they used what's called a conic coordinate system, and you won't find this in any textbook before. This is knowledge I have revealed to you for the first time. Okay, you've never even heard of a conic coordinate system before you've read this, whereby any location or conic curve can be described in space using the cone. For example, if we are observing a cone and the apex is on top with reference to our standing upright, then a random parabola is given by a cone rotation, a distance from the cone apex to the disk on which a parabola apex rests, and the distance between the cone apex and the parabola apex. So a particular point could be described by the intersection of these geometric objects and those cone geometric objects acting as locators on the cone itself. But to arrive at the cone, it is first necessary to produce the objects from which the cone is constructed. That is, a point, line, and circle. Okay, in fact, you don't even need the circle. But those three objects came before the base cone object. And in this diagram, I show you how you can locate the apex of the parabola, which is this black point, right? The clarity of ancient Greek thought has been unmatched by any who came before or after them. In the history of mathematics, no such clarity has been realized in the last 2,000 years. Let's look at some of the preliminary notions. And one of the most important is to understand what is a nomenon. It was first coined by Immanuel Kant, okay? And it's a perfect concept that exists inanimately and requires no prior existence or thought. So probably the most common example is the symptom of the incommensurable magnitude pi, right? It exists whether the ancient Greeks thought of it or not. In fact, even aliens can arrive at it because it's not an invention, it's perfect knowledge. It is a nomenon because it is a well-formed idea or concept that arises when an attempt is made at measuring a circle's periphery using its diameter. Whoa, you may exclaim, but where did points, lines, and circles come from? Well, all those are the focus of this chapter, which is how do we derive the 5 requirements from scratch? So what is a point? Let's see. A point is simply an idea of location or place. It is realized instantly when we ask the question where. The period or dot that is normally used to represent a point, that is this little dot here, is only a visualization or instantiation of the nomenon. The next logical idea that arises is a relation of one point to another. That is, how to get from one location to another. It begs the question, how to get there. In other words, what are the directions, okay? So now we're going to start off with a systematic approach. At this stage, right, so we know what a point is, and now the next thing we're going to do is see how to derive this first postulate here. It's not a postulate, the first requirement, I'm sorry. I don't want to use the word postulate anymore. It's the first requirement. Let it have been postulated to draw a straight line from any point to any point. It doesn't have to be postulated. It's going to be proved. Let's see how. Okay, so at this stage, we can't give precise directions yet, but we do observe that between any two locations or points, there are innumerably many paths. So if we look at this applet here, between any of 2 points, any of these 2 points here, there are innumerably many paths, but only one straight line path. So I could go like this to get to this point, or I could go like that. It's very easy to see that there are innumerably many paths. And for you to understand this, you need to read through this section very carefully. Don't skip anything, and I suggest reading it a few times. We also observe that any given path describes a set of directions from one point to another. And so a straight line describes a path between one point and another such that the direction remains unchanged. By the way, I do define all these words here, even though they are defined in the English language, I do define them from nothing. Path, direction, and everything else, okay? Direction is well defined. It is the how do I get there concept. And path is also well defined, okay? And if you read in here, you'll see all these definitions are defined from nothing. And you can pause and think about the definition of a straight line. Does it require any prior beliefs? No. Does it require any vague or mystical dogmas or axioms or postulates? The answer is no. And a straight line is the shortest path or distance between 2 points. So between any 2 points, there are innumerably many paths, but only one of those paths is unique in distance. This red object that you see here is not a straight line. It's just a visualization or instantiation of the shortest path between these 2 points. In other words, what is the main attribute of a line? The main attribute is distance. A line does not consist of points because points have no dimension. Points are just an idea of location, and there are innumerably many locations between this point and this point here. We can't reify them. Definitely not all of them, at any rate. Okay, in fact, the majority of them we can't reify. So a line does not consist of points. A line is the distance between 2 points, always, and it doesn't include those points. You get it? Okay. Now, so really, that's all that is a straight line. It describes a path between one point and another such that the direction remains unchanged. Very easy to reify, no problem at all. And the next, so that takes care of this requirement here, to draw a straight line between any point to any other point. And then we want to know if it's possible to do this, to produce to produce a straight line indefinitely. In other words, to stretch it or extend it or shorten it, right? And we can do that also. The second requirement states that a straight line can be extended indefinitely. The definition and proof of this requirement is amazingly simple. All one has to do to prove the second requirement is to consider a portion of any given straight line. In other words, if we look at this again here, we can just consider this portion of the straight line. We'll see that it's between this point, and it can be extended very easily. So what it says here, and since we know that a straight line exists between any 2 given points from the first requirement, we are done. So we first define a complete path as that path which starts at one point and ends up at the same point after it has traversed other points. And the third requirement, now for a circle, is given here. It's the shortest complete path from which the distances to a given point, called the center, are all described by the same straight line. And in the book here, I'll show you how to derive it. For example, that definition, if it wasn't stated the way it is, could mean that this here is a circle, because if this red line here lies on the surface of the sphere, every one of these points are the same distance from the center, right? So still, that wouldn't suit our definition of a circle, which you see in a plane, right? So the other requirement is that these points here must lie in a plane, not just on the surface of a sphere. Otherwise, we have what's called non-Euclidean geometry, yes? So once we've defined a circle, as we have over here in this requirement, then we can define a plane immediately, because it's just the indefinite area spanned by a circle of increasing radius, right? So it increases in both directions, and that's a plane. And so we have a plane. And in only a few pages, we have already derived the first three requirements from nothing. So if you look at this here, we've derived 1, 2, and 3, and to draw a circle with any center and radius. So nothing about axioms there or postulates. The fourth requirement states that all right angles are equal. And before we can prove this fact, we have to define what is an angle and several other geometric objects. So an angle is formed at the intersection of two lines. Now remember, we already have lines, so we're not just doing this on faith or belief, axiomatically, so to speak. We're not doing it that way. An angle is formed at the intersection of two lines, which is called the vertex, right? So the idea of an angle is this space between the lines, but it's still not well defined yet. We have to do more to well-define angle. For any angle to be measured, the vertex must coincide with the center of any circle, and one of the lines must coincide with a diameter. In other words, we're going to use our geometric object called the circle to well define our angle, okay? In other words, the measure of our angle, because now we only have a concept of an angle. The concept is that these are angles where the lines cross, okay? This is an angle, this is an angle, this is an angle, and this is an angle. But we haven't figured out a way to measure them, and that's what we do in the next step. We measure an angle by saying that an arc is the length portion of a circle path, also known as a periphery or a circumference, and then we come back and we say a ratio of magnitudes is literally the comparison of any two given magnitudes, and I've actually covered this in my chapter on how we got numbers. So you could go and look at that, but you don't have to, because I also define it here. I say it can be any length, mass, area, or volume. And what you do is simply take the ratio of the arc length to the radius, and that gives you the measure of the angle. So a measure of an angle is defined as a ratio of magnitudes where the antecedent, or the numerator, is the length of a circle arc subtended by the angle to the consequent, or the denominator, which is its radius length. And the radius is a straight line from the center to any part of the circle path. The vertex is always located at the center. So if we had to draw a line there and there, or between any 2 points on the arc, we'd have what's called an angle, right? So we cannot define an angle we cannot define the measure of an angle without using the geometric object known as a circle. So we've done all that. So we've defined angles and everything else. And now we're going to start moving towards what is the definition of a right angle, right? So see, you don't have to accept anything on faith or axiomatically. A right angle is realized by observing that 4 equal arcs correspond to 4 angles. Now you might say, whoa, what are equal arcs? Well, hang on, be patient, I'll show you. You have to look at the proof of this, and you have to use the fact that there is a property of symmetry. So in this part here, I prove that given any diameter, a line through the center partitions the circumference of a circle into exactly 2 equal parts. So this diameter divides into that arc and into this arc, which are equal by symmetry, right? And we know that the diameter subtends an arc that is half the circumference, and so we can show that the circumference of a circle can be divided into 4 equal parts. All right, and I'm not going to go through the whole proof here. You can read all this and see that you don't need axioms or postulates. And so once you've done that, then you've really shown that all right angles are equal to one another, which is this 4th requirement here, okay? So you're almost there. Now, to get to the 5th requirement, you have to define many other concepts, okay? So we need to define parallel lines, and what I'll show you, also you need to know the concepts of vertex, angle, arc, ratio, right angle, radius. All these have to be defined first, and I do that for you. I show you what is a transversal line from scratch, and then finally we get to parallel lines, right? So parallel lines are chords or lines that are subtended on equal arcs, okay? Equal arcs from the center. And then once you've got equal arcs, you can define everything else, such as co-interior angles, alternate angles, and look at the sum of co-interior angles, prove that it is 2 right angles, And all this is done way before the fifth requirement, okay? Because the fifth requirement has nothing to do with parallel lines, right? And finally, we get to the fifth requirement. So let's, oops, I think I skipped that. The fifth requirement. Yeah, the fifth requirement is stated in the elements in terms of only the co-interior angles. And this is the proof of the fifth requirement. It says the sum of co-interior angles on the same side of a transversal is constant. It doesn't say exactly this, but this is what it means. Okay, it can't mean anything else. And what this means is it does not matter if the lines are parallel or not, and it also does not matter how the transversal cuts the lines. All right, so what does the fifth requirement say? Let's just see. This is the fifth requirement. Okay. If the lines are parallel, then we are done. This is the proof of it. Let's just look here. I think I've got that somewhere. I thought I had it down. Let me just see where, if maybe it's this. No, it's not that one. Okay. So it looks like, right, it's not in here. It's in another applet. All right, no problem. But I do give you the proof here so you can go through it yourself. And I've painstakingly shown you in less than half an hour how you can systematically derive all of the 5 requirements from nothing, beginning with a point and building on the notion of a point. It should now be clear that there are no axioms or postulates in Greek mathematics. And naturally, Euclid didn't do this because it was done by accident. He'd done it on purpose. He defined these requirements first because what comes later in the elements in chronological order is the definition of ratio, and then later in the 7th book, the definition of number. So nothing was left to chance here by the Greeks. They defined everything systematically from scratch. Right, so now I hope that will give you sufficient food to think of, and in the next video, hopefully, I'll be able to talk about how we got numbers and explain to you this all-important chapter in the history of mathematics and what led to the discovery of the first and rigorous formulation of calculus. I am the great John Gabriel, the discoverer of the new calculus. Till next time, this is a New Calculus channel. I wish you goodbye.